Okay, welcome to Control Systems Lectures. I do apologize that this is not in the classroom because of the strike. However, I think it's a really good idea to have this particular lecture in as a video because it's so important, and there's some very important maths that you may be able to follow if you watch the video a few times and write down your own notes. All right, so I'm going to do 4 videos and this is the first one, and we'll do the Laplace transform of important functions. Right. So remember, we have our dynamic system, which I represent here with a box. This is our dynamic system. And we have an input signal into the dynamic system and an output signal. And normally we call the input signal u of t. So this is a function of time. It's something that starts now and develops over time. And it is an output signal y of t. Okay, so we want to know, how does the system respond if I change the input? And we will find that there are different categories of systems, and the next videos will deal with the different categories, but let's look at it in general. We describe the dynamic system with a set of differential equations. All right. So we have a set of differential equations, and we don't have any particular differential equation. We have ordinary differential equations, means they are linear. Okay, and these will look something like this. It will look like dy or a1 dy over dt plus a0y equals to b0 times u. So that's a first order, particular type of differential equation. It's a first order differential equation, for example, but we can have higher order differential equations as well. And because we can't deal with them very well in the time domain, we don't have manipulators that we can easily change around and solve for y of t. We make it more complicated by introducing the Laplace transform. And as a result, we have an input signal in the frequency domain and Laplace domain that we call u of s. And we denote this with a capital letter U. So here we have a lowercase u for the time domain and an uppercase U for the frequency domain. And we have an output signal y of s. And instead of a differential equation, we now have what we call a transfer function. And the nice thing is that the relationship between the output signal and the input signal is now a simple multiplication of the transfer function times the input signal. So that is really handy because now we can work with these signals. These will be simply polynomials, and we can manipulate them in different ways. Okay. So I need to talk about these important functions. Okay. And for this, I'm going to draw you a grid of important functions. So first of all, I would like to give it a name. And our most important functions in control systems is the step function. Okay. So I'm going to give you, for each function that I will introduce, I'm going to give you the name. And I will give you the time definition. So it's defined as, and I will call it this little funny symbol 1 of t to indicate it's a time function. And it is very simple. It is 1 if t is greater or equal to 0, and it's 0 for t smaller than 0. Okay, so it's not a terribly difficult function. If I can draw it for you, it looks very simple. It looks like that. So this is 1 of t, and it's 0 for t smaller than 0, and then it jumps up to 1. Okay, so this is the plot. So this is our time function f of t. Now, this function is normally our input function to our signal. So this is normally u of t. I'm just writing it small. I shouldn't write that because it could also be the output. But very often this is our experiment that we act onto the system. So for example, if we have a heater and we open the valve of the heater, we open it a little bit. So we're increasing it from, let's say, 0 to 1 within a very short amount of time. Obviously, it's never going to be an infinitely small amount of time. This one here jumps up, but it's good enough for us. Yeah, it's almost within an infinite short amount of time. I am increasing the radiator from 0, and I'm moving it up. I'm turning it slightly, and it goes up to 1. And then I want to know what happens to the output of my system. Okay, so we very often use this as an input function to our system. Okay. And now I need to know what the Laplace transform is of this function, and it's very simple. It is 1 over s, or 1 divided by s. Okay. So this is our all-time favorite, most important system for control. Sorry, signal for control systems. Okay. Another important input signal to our system is an impulse. So sometimes we don't put a step, sometimes we put a little pulse. And we can't really do an impulse. The impulse is defined as a delta impulse, delta of t. And it is infinity for t equals to 0 and 0 elsewhere. So it's a very funny signal. It doesn't really exist in real life, but we can do something that's almost like an impulse. We can do a little pulse. So it says, indicate this with an arrow pointing up at time t equals to 0. There's a little arrow going up, and this is delta of t, and it goes up infinitely, and everywhere else, this function is 0. So this, for example, we could do is if we have a tank and we have an inflow into the tank and an outflow, and we have a certain concentration. Sometimes you want to do something that's called a tracer test. We want to know what happens to our concentration if we, for a very short period of time, spike it. Yeah? So let's say we have an acid inflow, and we're going to increase the acidity for a very short amount of time. And it's not exactly an infinite short period, but it's for a short period, and it looks like a little pulse here, but we pretend it's an impulse. And I want to know what's the impact of the concentration at the outflow of the tank. And this would be an example of a pulse, and we model this often with an impulse. And the nice thing is that the Laplace transform of this impulse is very simple. It is 1. And that is because we integrate over the function, over the entire spectrum here. And we have, if we integrate this pulse here, the area of this pulse is 1. And we do this at time t equals to 0. We multiply this in the Laplace transform with e to the minus st, and it's 0 elsewhere, and it's this area 1 at time t equals to 0. So we end up with this value here of 1. So that's very nice. We do have a pulse. That is an interesting, so that's almost like an impulse. And we define this as delta not delta. The delta was our impulse. Let's call it P of t. And this is some certain amount h. If t is between 0 and a time tw, and it's 0 elsewhere. So instead of having this infinitely high pulse, we have a pulse that looks like that. Between time 0 and tw, it is h, and it's 0 elsewhere. Yeah? And the Laplace transform isn't as nice as it is with these two previous sections. It is 1 minus e to the minus tws times h divided by s. Okay, so this is effectively the step going up, and this is the step going down with a time delay. Okay, so that's something we would like to have as an input function. We have a signal that we call a ramp. Yeah? And that can be both an input signal. Sometimes we don't like to put a pulse onto a system because we may damage our actuator, our valve, or our motor. So what we would like to do is we like to ramp it up slowly. Yeah? And it could also be an output, which we'll see later in the video in an integrating process. So the ramp function can be an output signal, can also be an input signal. Okay? And it's defined as r of t equals to t, if t is greater than 0, and 0 elsewhere. And you can easily imagine what it looks like. It's 0 if t is smaller than 0, and then it goes up as a linear function. And the Laplace transform of this is not terribly complicated either. It's 1 divided by s squared. All right, so these are possibly our input signals, and what we often have as output signals resulting from very simple processes such as first order processes are decaying exponentials. Okay, and this function is defined as e to the minus t divided by tau. So this is a decaying exponential, and it looks like that. We have to multiply it with the step transform because it's also it's 0 for times before time 0, and then it goes up to 1, and then it becomes a decaying exponential. It looks like that. Let me draw this so you see exactly what it looks like. We go up to 0.1, and then we have this decaying exponential, and we can draw a tangent here we can draw the slope at time t equals to 0 of this function here, and when we hit the 0 amplitude, we measure the time constant tau. Yeah? And it's a decaying exponential, it goes to 0. And the Laplace transform of this function is tau divided by tau s plus 1. Sometimes we don't write it like that. Sometimes we write it as e to the minus a times t. So instead of having minus t divided by tau, we have minus a divided by t. So a equals to 1 over tau. We get the same form, only the Laplace transform looks slightly different. It's 1 divided by s plus a. Okay. So it's exactly the same function. The only difference is that we define this in this representation. We have e to the minus at, and here we have e to the minus t divided by tau. So there's a slightly different factor in front of the s here, and we write it slightly differently, but it's exactly the same function. And this is usually our output signal y of t, for example, for a first order process. And the reason why I'm mentioning this here, because it's very difficult to imagine this to be an input signal. What kind of experiment would I have as an input? I would have to open something and then close it with an exponential function. So this is not really what we do as an experiment. However, this is the most common, or it's a common output signal of our process, and for example, for a first order process. Okay? And another output signal that I have is a sine wave I can have. So it's the sine. And you all know what a sine function is. So this is A is the amplitude times sine omega t. Use a different pen color now. And what does it look like? And we also have to multiply this with a step function. So it has to be 1 for t is multiplied with this function here. It's 1 for t greater or equal to 0, and it is 0 before time 0, before I start my experiment. Okay. And you know what this looks like. This is a sine function, so it's 0 before 0, and then it oscillates around the time. And we have an oscillation period of t. The relationship between t and omega, here I have sine of omega t. The relationship between omega and this oscillation period is t 2 pi divided by omega. Yeah, just so that you know. And the amplitude I can read out at the peak of the oscillation. And the Laplace transform of this function is a times omega s square plus omega square. Okay, so that is a very important output signal. So all these signals can be inputs and can be outputs, but very often the step, the impulse, the pulse are the inputs, and decaying exponentials and sine waves are the outputs. Okay. And this is the first video. These are the most important functions of the Laplace transform, or important signals that we're going to use later on. So it's really important to memorize them and to recognize them. So you don't have to know them by heart. It does help, but you should definitely have this table here somewhere in your notes. It's very important. Okay, see you for the next video.